We present visual surface wave elastography, a method for estimating subsurface material and geometric properties of objects from monocular video. Our primary motivation is to infer mechanical properties of biological tissue from video to enable inexpensive at-home health monitoring. Specifically, we recover the stiffness and thickness of soft tissue. These biomarkers are useful for assessing health conditions including tumors, musculoskeletal degeneration, and liver disease. For example, by observing the expression of waves on the surface of the leg, we estimate the stiffness and thickness of the soft tissue at multiple regions. The thickness tells us how deep below the surface the bone is, even though we can't directly observe it. Waves contain information about the subsurface material and geometric properties of their environment, called the wave medium. Linear elastic waves can be decomposed into modes, which occur at different wave numbers denoted by gamma and different frequencies denoted by omega. A wave number is like a frequency, but for space instead of time. Wave dynamics extend well below the surface and are influenced by subsurface features of the wave medium. The material properties and thickness of the soft tissue determine which wave number frequency pairs are allowed to propagate as waves. This is compactly described by the dispersion relation. Shown here by white curves, the dispersion relation of a given wave medium is a multi-valued function that tells us which wave number frequency pairs are permitted by the medium. This is the observable that we use to perform inference. However, because we only see the surface expression of waves and cannot expect to comprehensively excite all possible wave modes, the observed dispersion relation is often incomplete. To find a hypothesis that matches our observation, we use physics-based simulation. We model biological tissue as a layered medium, with a soft layer sitting atop a much stiffer layer of bone. Our method leverages this model to estimate the thickness and stiffness of soft tissue that most closely agree with the dispersion relation observed from the video. We start with a video of small amplitude waves traveling across the surface of the material. We use phase-based motion processing to extract the displacement field for each frame. In this example, waves are propagating in the horizontal direction from right to left. We apply FFT along the time dimension to separate the observed wave modes by frequency. For each separated wave mode, we apply a second spatial FFT along the direction of wave travel to understand which wave numbers are associated with each frequency. By averaging over image rows, we obtain our video observed dispersion relation. This observed dispersion relation is the input to a physics-based optimization procedure where we determine the tissue thickness and stiffness that best agree with the dispersion relation observed in our video. We tested our method on a real gelatin phantom and a simulated human leg with anatomically accurate geometry. First, let's talk about the gelatin phantom. A phantom is a material used to emulate the mechanical properties of biological tissue. Gelatin is commonly used as a phantom, but its stiffness is dependent on both temperature and frequency. The gelatin is initially set in the fridge, so it starts out cold and stiff, but as it warms up to room temperature, it softens. Our method recovers stiffness within 1.2% error, even as it changes with temperature. Our method also recovers the correct thickness for samples that differ by only a few millimeters. Now, let's talk about the anatomically accurate simulated leg. This experiment challenges our method because anatomical geometry is messy and deviates from some of our idealized assumptions. First, we look at two general regions, the upper calf and lower calf. Our method accurately recovers the correct stiffness and gives thickness values around the true average values in each region. Next, we zoom in to the upper calf. We slide the signal window horizontally across this broad region, estimating the tissue parameters at each horizontal position. Here is the recovered thickness, along with the true distribution of thickness in each of these windows. Finally, we zoom in to the extremely thin tissue near the ankle. For each signal window, we show the recovered thickness along with the true thickness distribution over each window. To learn more about visual surface wave elastography, please visit our project page.